Hello all. Welcome to our fourth lecture on space robotics and autonomy. So in the last lectures, we discussed about the kinematical analysis of a robotic manipulator. We went into the details of forward kinematics, inverse kinematics, differential kinematics. And we discussed the need for redundancy and how we can avoid singularities. Today I'm going to introduce you the concept of manipulator mass distribution, and we will see how we can apply the concept of mass distribution to define the inertia tensor or the inertia matrix of the manipulator. Then we will discuss the parallel axis theorem, and thereafter we will discuss the modeling, that is the dynamical modeling. I'll introduce two methods, the Lagrange-Euler method and Newton-Euler method. We will discuss in detail the Lagrange-Euler method, and we will only discuss very briefly the Newton-Euler method, mainly to understand the difference between these two approaches. Let's start with mass distribution. So let's consider a rigid body. A rigid body can be treated as a collection of n-point masses. Therefore, we can say that a rigid body is nothing but a continuous distribution of mass. In the case of a rigid body that is free to move in the three-dimensional space, there are infinite number of rotational axes. For example, if you take a look at the rigid body illustration in slide 3, you can very well see that we can define any axis of rotation with respect to which this object could rotate. Now, if we consider the rotation of this body with respect to an arbitrary axis, we need to develop a method that can be used to characterize the mass distribution of this rigid body. And this is what we are going to do in the next few minutes. Let's consider this rigid body that has a single degrees of freedom. So we are going to analyze the mass distribution based on the illustration for a random rigid body shown here. Let's consider that the axis xi, yi, zi for this rigid body is arbitrarily chosen, and the object is free to rotate with respect to its zi axis. Now let's consider an arbitrary point P anywhere along this rigid body. Now, with respect to this point P, if you define a differential volume, say delta V, then delta V is nothing but the product of dx, dy, dz. We know the relation connecting density, mass, and volume. Density is mass per unit volume. Therefore, we can extend this definition to the three-dimensional object that is free to rotate in the three-dimensional space by the definition integral over V, rho dV is integral over V, rho times, that is density times, the differential volume, which is dx, dy, dz. So this is nothing but the mass of the object. Now let's extend this concept of mass distribution to define what is the inertia matrix, also known as the inertia tensor. Now for this we need to start with the basics of moment of inertia. So what is moment of inertia? Well, moment of inertia is a measure of a body's resistance to changes to its own rotation. So if you consider the rigid body that was shown in slide number 3, with respect to this diagram, let us discuss two cases. One in which the rigid body is free to rotate with respect to an axis positioned at its center of mass. And the second case, let it be as shown in slide 3, that is, it is free to rotate with respect to an arbitrary axis. Now in these two cases, which case would have higher moment of inertia? So if the object is free to rotate with respect to its center of mass, then the moment of inertia will be lower compared to the scenario where the object is free to rotate with respect to its arbitrary axis of rotation. So let's take a look at the slide number 3 again. So here, if we consider the rotation with respect to this arbitrary axis of rotation, then the object will have higher moment of inertia compared to the case when the object is rotating with respect to its own center of mass. And this is because the farther you move from the center of mass, the greater will be the moment of inertia. Now next, let's try to analyze the moment of inertia based on the energy, that is, based on how we analyze the kinetic energy. Now for that, let's consider a simple example of a thin rod. Let the rod be of, say, length r, and let it be pivoted at one end, and let the rod be carrying a point mass at its other end. So this rod is basically free to rotate with respect to its pivoted point. And we know that the linear momentum of this body is defined as a product of mass times its linear velocity. That is, linear momentum is mv, or mass times the linear velocity. On the other hand, the angular momentum is the product of the inertia matrix that we are going to define soon times the angular velocity. So let's see how we can find an expression for the inertia matrix. Now for that, we are going to start with the expression for the kinetic energy. So we know that kinetic energy is half times the mass of the object times the square of its linear velocity, or half mv square. And we know that the linear velocity v is the product of the radius of rotation, that is r, times the angular velocity, or simply v is r omega. So if I substitute for velocity in the expression for the kinetic energy, I get the expression for kinetic energy as half m r square times omega square. So I can write this as half mr square times omega square. Here the term mr square is defined as the moment of inertia, and it plays the same role as the mass m in rotational dynamics. Therefore, we can say that inertia matrix is a generalization of the scalar moment of inertia, or the mass moment of inertia, and it depends on the location and orientation of the reference frame. Or in other words, the inertia matrix is not a fixed value. depending upon the frame of rotation based on its location and orientation, accordingly the inertia matrix will change. Here you need to note that the scalar moment of inertia, which is also known as the mass moment of inertia, that is the product mr square, is defined with respect to a fixed rotational axis. This is the scalar moment of inertia. Scalar moment of inertia is defined with respect to a fixed rotational axis, and its SI unit is nothing but kilogram meter square. On the other hand, inertia tensor or the inertia matrix that we are using in the context of a robotic manipulator is defined with respect to any arbitrary rotation axis. Thus, inertia matrix or inertia tensor is a generalization of the scalar moment of inertia. Here in slide 5, we define the inertia tensor as a 3x3 symmetric positive definite matrix. So by this definition, what we mean is inertia matrix is a square matrix and it's a symmetric matrix, which means its off-diagonal elements are identical, and it is a positive semi-definite matrix. To understand that, let's consider a vector, a non-zero vector, which contains only real terms. If we are able to find a vector x, then if x transpose Ix, that is x transpose times the inertia matrix times the vector x, if this is always greater than or equal to 0, then we say that the inertia matrix I is a positive semi-definite matrix. And here we have the definition of the inertia matrix I. Please note that this is not the identity matrix I, but I is the standard notation we use for inertia matrix as well. So this is a representation of the inertia matrix. Now let's try to work out the expressions or the individual elements of the inertia matrix. So as you can see in this slide, its diagonal elements, that is Ix, Iy, Iz, are referred to as the mass moments of inertia, and each has its own definitions. For example, Ixx is defined as a triple integral over V y square plus z square, the sum of this term times rho dV, where rho is the density and the term y square plus z square is the square of the perpendicular distance from the corresponding axis. So basically we know rho delta V is nothing but the mass, and y square plus z square is the square of the perpendicular distance from the corresponding axis of rotation. Similarly, we have the term Iyy, which is again the triple integral over V x square plus z square times rho delta V. You can also find the value of Izz, which is the triple integral over V triple integral over V x square plus y square times rho delta V. Now if we define the off-diagonal elements, these are referred to as the mass products of inertia, and we denote by the terms Ixy, Ixz and Iyz. Ixy is defined as the integral of xy times rho delta V, and Ixz is the integral of xz times rho delta v. Iyz is the integral of the term yz times rho delta v. Here we can find out an orientation frame such that the terms Ixy, Ixz and Iyz can be set to 0. And the axis of the reference frame, when so aligned, is referred to as a principal axis. So if we have an inertia matrix with all its off-diagonal elements set to zeros, then it means basically the inertia matrix is based on the principal axis of rotation. And we call the corresponding moment of inertia as the principal moment of inertia. Now let's move on to the parallel axis theorem. We know that kinetic energy has two components. One is its translational part and the other is its rotational part. And inertia matrix is actually associated with the rotational part of the kinetic energy. Parallel axis theorem is used to find how inertia matrix changes under translation of the reference coordinate system. Let me repeat that. So we use parallel axis theorem to find how the inertia matrix will change if the reference coordinate system undergoes translation. Thus, we can use parallel axis theorem to relate the inertia matrix in a frame with origin at the center of mass to inertia matrix with respect to any other reference frame. So in the case of a robotic manipulator, the frame of reference, we know that it's nothing but the z-axis, which is the axis of rotation, and x and y axis are the corresponding orthogonal axis for this reference frame. So if you apply the parallel axis theorem, where you know the inertia matrix with respect to the center of mass of the ith link, and say if m is the mass of the ith link, and if say r is a position vector that represents the distance from the center of mass to the joined coordinate frame, then we can get the inertia matrix with respect to the joined coordinate frame as I suffix IR is I suffix IC plus MR square, where I suffix IC is the inertia matrix of the ith link with respect to its center of mass, that is center of mass of that ith link. M is the mass of the ith link, and R suffix I is a position vector that represents how far the center of mass of the ith link is from its axis of rotation, that is the joint axis. Next, you have a problem. Well, this is a case of an 8 degrees of freedom space station remote manipulator system that we discussed in week 1. So here you are given the inertia matrix with respect to the center of mass of each of the link, and you're asked to apply the parallel axis theorem to determine the moment of inertia of each of the link with respect to their joined coordinate frames. So to find this, you're also given the additional details such as the position of each of the link's center of mass and the corresponding masses of the individual links. This being an 8 degree of freedom system, you have 8 individual masses, and you're also given the corresponding XYZ coordinates for the center of mass of each link. And using the inertia metric, that is, this is based on the principal moments of inertia, you are asked to work out the new moment of inertia with respect to the joint coordinate system. And you can find this using the parallaxis theorem that we just discussed. Let's move on to the dynamical modeling of a robotic manipulator. So dynamical modeling deals with mathematical formulation of various equations of motion of the arm. That is, we are trying to express what forces or torques causes the motion of the robotic arm. And we use dynamical equations for simulating the behavior of the robotic arm. And dynamical equations are inevitable if you are trying to design the closed loop controller, and we can use it for evaluating the kinematical design as well as the structural analysis. The dynamics of a robotic manipulator can be classified as forward dynamics and inverse dynamics. In forward dynamics, we calculate how the robotic manipulator will move under the application of certain joint torques. Or in other words, we can say that in forward dynamics, we know what are the different joint torques. And based on that information, we can calculate the joint angle, the corresponding joint velocity, and joint acceleration. And we use forward dynamics for simulating a manipulator. On the other hand, in inverse dynamics, we are actually given, or we know, what are the different joint values, that is the joint angles, the corresponding velocity and acceleration. And we are required to find what are the different joint torques that will result in such a value for the different joint angles and their velocities. And inverse dynamics is what we use for controlling a robotic arm in real time. Thus, we say that the dynamical behavior of a robotic arm depends on 1. How accurate your dynamical model is, 2. How robust your controller is. So to get the best performance, we need to ensure that the dynamical model is as realistic as possible, and 2, the controller you design is as robust as possible. Thus, we can make sure that by having a well-defined dynamical model, we can design a closed-loop controller that will take into account the dynamical model, which in turn is defined using the different geometric or the inertial parameters of the link. There are 2 different approaches that are widely used for the dynamical modeling of robotic manipulators. One is called the Lagrange-Euler method, and the other is called the Newton-Euler method. The Lagrangian mechanics is basically a reformulation of classical mechanics that combines conservation of momentum with conservation of energy. We will be discussing in detail Lagrange-Euler formulation. And we will not be going into the details of the derivation of Newton-Euler formulation, but I'll just briefly tell you the difference between these two approaches. So let's start with the Lagrange-Euler method. The Lagrange-Euler method, the approach at the process of developing the mathematical model, is simple and systematic. And when we derive the Lagrange model, you will see that the model itself is a highly nonlinear model that takes into account the effect of inertia loading, coupling effect between joints, and also the effect of gravity. The magnitude of the torque or the forces depends on the manipulator's physical parameters, such as the sizing of the links, the type of the actuators or the motors that we use, the instantaneous configuration of different joints, their joint velocities and accelerations, and also the type of the payload the arm is carrying. So in Lagrange-Euler method, we start by defining the Lagrangian function, which is a function of the energy. The Lagrangian is defined as the difference between the kinetic energy and the potential energy. So here I'm using the notation K for defining or for the kinetic energy, and I'm using the notation V for the potential energy. Using the Lagrange-Euler method, we can develop the dynamical model that will be suitable for designing the closed-loop controller in the state space form. We will discuss the state space form and other approaches later when we go through the control theory. So for the time being, let's concentrate on the modeling rather than the control. So using the Lagrange-Euler method, we can define the generalized expression for the joint torque by the equation tau suffix I, where I represents the ith joint, using the relation d by dt of dou L by dou theta dot minus dou L by dou theta suffix I. Let me repeat it. So the joint torque of the ith joint is defined as d by dt of dou L by dou theta I dot minus dou L by dou theta I. Here L is a Lagrangian, theta I is a joint angle of the ith joint, and the term you see in brackets are the partial derivatives. So the first term is a partial derivative of the Lagrangian with respect to the joint velocity, that is theta I dot, and the second term in the bracket is a partial derivative of the Lagrangian with respect to joint angle theta I. So this is how we define the generalized expression for the torque using the Lagrange-Euler method. We know that energy depends on the kinetic energy as well as the potential energy. And of course, in the case of zero gravity conditions, you will not have to take into account the term V. And for the kinetic energy, you need to take into account the total kinetic energy of all the links for this manipulator. And as I said earlier, kinetic energy itself consists of its translational energy as well as the rotational energy. So we need to take into account both terms. So the translational energy is obtained by concentrating the entire mass of the arm with respect to the center of mass, and then the rotational energy of the body is also obtained with respect to its center of mass. Let's take a look at the expression for the total kinetic energy. So if you take into account the translational component and the rotational component, we can write the total kinetic energy as K is half m V transpose V plus half omega transpose I omega. We get this expression from the general relation. So for example, we know that scalar moment of inertia, if you use a scalar moment of inertia, kinetic energy can be expressed as half mv square plus half I omega square, right? Now, if you're using the inertia matrix or the inertia tensor, the kinetic energy is expressed as half mv transpose V. Rather than V square, we write V transpose V plus half omega transpose I omega, because this is a more generalized form. So here in equation 1, the expression of the kinetic energy contains a product V transpose V, which is simply the square of the velocity vector V. That's a translational velocity. Here you need to note that the product V transpose V will remain the same. The magnitude will remain the same irrespective of the frame in which this vector is expressed. Because in the case of translational velocity, changing the frames will merely multiply the vector by a rotational matrix. It doesn't change the magnitude or the value of the vector. On the other hand, with the rotational part of the kinetic energy, the rotation or changes in the coordinate frame will have an impact, and this is why here for the second term we do not write half I omega square, because we have to take into account the changes in the coordinate frame, and therefore we write the second component of the kinetic energy as half omega transpose I omega, where omega is a vector representing the angular velocity. Here you need to note that the triple product omega transpose I omega will be the same in all frames. So omega will change as you change the coordinate frame, whereas the triple product omega transpose I omega will remain the same for all frames. The inertia matrix and the angular velocity can be thus computed with respect to the coordinate frame that is attached to the corresponding link. So let's take a general case where we have a manipulator with, say, n degrees of freedom, or in other words, we have n links. And let's take the vector q that represents the generalized position coordinates of the end effector, and let theta be the vector that represents the different joint variables or the joint angles. And we have already seen the relation connecting the position vector of the end effector with the joint angles using the Jacobian. So we can write Q as J theta, where J is a Jacobian matrix which itself is a function of the joint angles. So that's the reason I write J as J of theta. Of course, you don't have to write J of theta because it's implicit that Jacobian J is a function of the different joint angles. Now, if I find the time derivative of q, we know q dot is j theta dot. This is a linearized form. And we know that the velocity q dot has its linear component as well as the angular component. So I can write q dot as vc suffix I and omega I. And similarly, I am decoupling the Jacobian corresponding to its linear part as well as the rotational part. In the case of space manipulators, if the angular velocity is measured with respect to the inertial frame, then of course we need to express it in terms of the frame that is attached to the link. In that case, we will have to consider the coordinate transformation, and therefore the angular velocity of the link, which is denoted by omega suffix I, will be written as Ri transpose omega naught, where omega naught is the angular velocity with respect to the inertial frame. R suffix I is a coordinate transformation matrix, and omega I is the corresponding angular velocity of the ith link with respect to the frame attached to its joint coordinate system. Of course, we need to use this transformation only in cases where we measure the angular velocity with respect to the inertial frame. So for rest of the derivations in the next slides, I'm using this because later on when we discuss space free flyers, we will be using or we will be measuring the angular velocity with respect to the inertial reference frame, which is a frame with center attached to the center of Earth. So let us use that for the generic case. And now I can write the linear component of the velocity, that is Vci, as the component of the Jacobian times theta dot. Of course, there is no change, so it's just extracting that term from the previous slide, the expression for Vci. And next, if you write the expression for the angular velocity omega I, then with this additional transformation, we have the relation Ri transpose j omega I theta dot. So this is a generic expression for the linear velocity as well as the angular velocity. Next, what I'm doing is I'm trying to find the total kinetic energy for the manipulator. And for that, I write the expression for the kinetic energy as half summation, where I can vary from 1 to n, the linear or the translational part of the kinetic energy plus the rotational part of the kinetic energy. So that is mi v transpose v plus omega transpose I omega. Here m suffix I is the mass of the ith link and I suffix I is the moment of inertia of the ith link. So what I'm doing next is I'm substituting the expression for the linear velocity and the angular velocity for the ith link from equation 2 into the expression for the total kinetic energy. So when you do the substitution carefully, you will see that you have a term j theta dot transpose. So you have to be careful when you take the transpose of this product term. So generally, if we have, say for example, uh, a product AB, and then you try to take the transpose of that product, that is AB whole transpose is actually B transpose times A transpose. So we are applying that concept here, or that rule here, to expand the expression for the kinetic energy. So if you do that, then I can write the total kinetic energy in a simplified form by grouping the terms that are common to theta dot transpose and theta dot. So basically I'm pulling out the terms that are common to theta dot transpose and those terms that are common to theta dot, and writing the expression for the total kinetic energy in a more compact form. Here I use the notation d of theta for the entire summation. Thus I can say that the total kinetic energy of the manipulator is given by K is half theta dot transpose d of theta times theta dot, where d of theta is an n by n matrix, nothing but the inertia matrix. So this matrix is a symmetric positive definite matrix, and this is your inertia matrix or the inertia tensor. If you need to consider the potential energy, we know that in the case of a rigid body, the potential energy, the only source of potential energy is the gravity, and this in turn depends on the joint angles. Because we know that based on the value of the joint angle, accordingly the position of each of the links would change, which means the height of the center of mass of each link will change based on the corresponding joint angles. So you can calculate the potential energy, which is a product of mass times gravity times the height of the center of mass. And the height of the center of mass of the individual links changes based on the joint angles. Of course, for space-based applications, we just consider only the kinetic energy, because we can treat the potential energy term to be zero under zero gravity conditions. So you get the general expression for the joint torque as tau suffix I is d by dt of dou k over dou theta dot minus dou k over dou theta, where dou k is a partial derivative of the kinetic energy with respect to theta dot or theta for the individual terms. In general, we write the Lagrange-Euler equation for the dynamical model of an arm by the expression tau I is d theta theta double dot plus h of theta theta dot plus b theta dot plus g of theta, where d of theta is the inertia matrix, which is a symmetric positive semi-definite matrix, and it's an n by n matrix. G of theta is an n by 1 gravity loading vector. It is a function of the joint angles. The term B is the actuator's viscous damping coefficient, and the term H is actually representing the nonlinear Coriolis and the centrifugal forces. Here the terms H and G are the nonlinear terms. Thus we see that the Lagrange-Euler equation of motion is a second order differential equation, and it is a coupled highly nonlinear equation because it takes into account the coupling between the different joints, and of course this model takes into account the inherent nonlinearities of the system. So we can say that the Lagrange-Euler method is a nonlinear model that takes into account the different nonlinearities of the system. Here you will see that the coupling effect, the nonlinearity due to the coupling effect, will be more dominant for the positioning links of the arm rather than the effect of the nonlinearity associated with its wrist. And this is because the moment of inertia associated with the links of the arm is much higher. One downside of the Lagrange-Euler method is that in terms of the computational load, the computational complexity is of the order of n to the power 4, where n is the total degrees of freedom. So if you look at various textbooks on robotic manipulators, the kinematical and the dynamical modeling, you will see that authors tend to quote that the computational complexity for Lagrange-Euler method is significantly higher, and that is because it depends on the fourth power of the total degrees of freedom. In fact, these methods, that is the Lagrange-Euler method, this was actually proposed several decades back, and at that time, using the computers we had then, this was a computationally intensive approach. But today, we use the Lagrange-Euler method very widely because we have fast processing computers. Therefore, I wouldn't really say that this approach is not used, because we do use it on a regular basis because we do not have much complexities associated with the computational load for running this dynamical model for such arms. And interestingly, for your coursework, when you generate the closed loop control algorithm, the dynamical model that I have provided you is in fact based on the Lagrange-Euler method. And if you are able to design a good controller, you will see that within few seconds you can actually visualize the performance of your closed loop system without much delay. So Lagrange-Euler method is widely used method despite the fact that it could be computationally intensive based on the type of the processor or the computer you use. Let's move on to the second method, that is the Newton-Euler method. Here, as I said earlier, we will not be going into the details of the derivation. Let me just briefly tell you how Newton-Euler method is different to Lagrange-Euler method. So in the case of Lagrange-Euler method, we know that we use the 4x4 homogeneous matrices. So basically it is based on matrix analysis, right? Your inertia matrix is a matrix formulation. So is the case with any kind of transformation matrix or the coordinate transformation matrix that you might use. So in the case of the other method, that is Newton-Euler method, we do not use matrix formulation. Instead, we use vector formulation, and it is based on the recursive approach. That is, we make use of the forward and the backward recursive equation. So we can say that because the Newton-Euler method make use of the recursive approach, It is computationally faster than the Lagrange-Euler method that make use of matrix analysis. But of course, if you look at the details of the Newton-Euler method, the derivation as such is much more complex because we make use of vector cross products. So in Newton-Euler method, we use a set of recursive equation. The forward recursion method is used to propagate the kinematics information, that is the information on the linear velocity, angular velocity, linear acceleration and angular acceleration with respect to the center of mass of each link. This information is propagated from the base to the end effector using the forward recursive equations. On the other hand, we can use the backward recursive equations for propagating the dynamical information from the end effector to the base. Thus, in this approach, we use a set of recursive equations that are applied to the robot's links in a sequential manner. So if you compare the two methods, one can say that, well, Newton-Euler method has computational advantage over Lagrange-Euler method, because here in this approach, the computational load is linearly proportional to the total degrees of freedom of the system. And it is independent of the configuration of the arm. So one can say that, yeah, we can use Newton-Euler method for real-time application, but from my experience, I would also strongly recommend you trying both Newton-Euler method as well as Lagrange-Euler method. So when you work on your coursework, you will really experience the benefits of the Lagrange-Euler method, because the dynamical model that I have provided is based on the Lagrange-Euler method, and this will really help you take into account the different nonlinearities, even though you are designing a linear proportional integral derivative or a PID controller. So even with a linear controller, if your dynamical model is a sophisticated one, you can achieve good performance. We will discuss the details of control in the next lecture.